All right, good morning, everybody. Let's start our discussion for today. So today is our second lecture on chapter 10. As I mentioned in the email yesterday, chapter 10 is a quite complex chapter with new concepts and we need to derive new equations to calculate both chemical potential, fugacity coefficients, and other related quantities. So try to spend enough time reading the textbook and go over the lecture materials we have, and try to let me know if you have any difficulty in understanding those concepts. It should take some time to appreciate those new quantities and figure out what is going on with those new concepts and how do we calculate those quantities using the previous materials, mainly about PVT calculations. So if we have a quick recall of what was discussed 2 lectures ago, we were mainly talking about moving from the pure system, whether it's a, a pure liquid phase or pure gas phase, but we don't have any mixture of different species or different phases. So purely one single component in one single phase. So over there, if we were looking at the properties, then we understand that we have the 4 energy equations, like I highlighted over here on this slide, and then we have the 4 derivative, which will tell us what would be the independent parameters to manipulate if we need to understand the property of that. For instance, we know that the Gibbs energy shall be the function of temperature and pressure, right? And only temperature and pressure. This is pure component, pure phase. Now move forward. Now we have the uh, mixtures, and the mixtures could be coming from the mixture of species. Say I have one single liquid phase, but I have multiple liquid molecules, water and ethanol, for instance. This is one case of the mixture, and we could have the other type of mixture. Say I still have pure water, one component, but I can have the liquid and vapor at equilibrium. So that is also the typical mixture we need to understand. And if that is the case, then we need to introduce the number of composition, those DMI, those values. So if we uh, try to round down the equation for the 4 energies, then we realize that now most likely we need to introduce the other independent parameter. Say for the Gibbs energy, it shall be the function of temperature, pressure, and the number of species, their respective composition. And over there we have a new definition called chemical potential, which is the partial derivative of those corresponding energy equations with respect to the composition Mi. And like we discussed, we need to pay attention to see what would be the independent uh, parameter to each of those energy equations. So here, for the Gibbs energy is temperature, pressure, and the composition. For the Helmholtz, it would be temperature, volume, uh, entropy and pressure, and entropy, volume, and so on, right? And we also emphasized that when we have this temperature, pressure, number of composition as the parameters to manipulate, then we have the correspondence of this so-called partial molar property. And using that criteria, we realize that only the chemical potential definition through Gibbs energy should be qualified for the partial molar energy. So we also call this as the partial molar Gibbs energy. Okay. So here is also a very important equation. And I believe that the textbook is using this correlation for the discussions in chapter 10, but here we try to explain a little bit more of how we can correlate the chemical potential to the PVT. So if you recall, we had the discussion that now if I have the definition of chemical potential, then we have the very general requirement, try to put it down as the function of temperature, pressure, and compositions. And over there, we received the first useful equation for the chemical potential calculation, which is partial derivative of chemical potential over pressure at fixed temperature composition. This should be partial molar volume, right? So I hope you see some potential mass manipulation that now we have this equation. We might want to replace this chemical potential by partial molar Gibbs energy. So somehow we are going to have the equation of partial molar Gibbs energy would be correlated as a function of the partial molar volume at some point. Okay, we will come back on this equation later. But that is the trend that we shall be expecting. And move on, we also discussed that now we have the mixture components or phases, then what is the working criteria to determine whether the system is at equilibrium or not. Think about the criteria for equilibrium. We were talking about the driving force. We have three potential driving forces, right, listed over here. This is why to correspond to those driving forces, we have the following requirement in order to determine whether the system is at true equilibrium or not. So here we need to satisfy for any system of mixture phases, we need to satisfy all the three equations. One is the temperature, the other is the pressure, the third shall be the chemical potential, and we need to satisfy the chemical potential for each component in the system. So we are not having three equations, but we have three sets of equations. So that is the other one. And then we know that temperature and pressure shall be easier to monitor or measure in the lab, but chemical potential is not the case. So this is why we try to determine how we are going to measure the chemical potential or calculate. So this was the discussion we had when we were looking at this equation, right? Like I mentioned, this equation is coming from the very general discussion pattern. Now we have this TP, MI. Now we try to see what would be the full derivative of this chemical potential, and we quickly receive this first working equation. So now we understand that the partial derivative of chemical potential with respect to temperature and with respect to pressure shall be the partial molar volume. Then the next step is we receive this working equation. We try to have some test on the simplified cases. So the first candidate is, of course, always ideal gas. So this is why we moved on to utilize that equation for the ideal gas. So over here, we need to utilize the ideal gas equation. PV is nRT, and now it's easier to write down this as PV is N, and what would be the total RT, right? Or N total is the summation of MI, I think. Well, it goes from 1 to M. And then we can replace this total volume by the equation over there, and then we can take the partial derivative. So pay attention to this equation. I explained in last lecture how do we have this equation. So now we know this partial molar volume is RT over P for the ideal gas. Then we move on, we have this equation. Again, this is the ideal gas. And then we manipulate, we divide yi. So here, that we try to have one extra note. So if we are talking about a yi, this implies that we are looking at the gas phase. If we are talking about the xi, this is talking about the liquid phase. Okay. So we divide both sides by yi, then we are looking at the partial pressure of that component I in the gas mixture phase. This is the partial pressure of component I. Then we receive this very nice equation. Okay, this is the fourth derivative of chemical potential for component I. If this is the ideal gas phase, then it is simply expressed by RTD log the partial pressure. Okay, so then we need to look at how do we run this integration, right? So this is the equation we have, equation 2, and then if we integrate this equation from some initial reference state, and now we call the standard state again. Over here, try to recall what is the definition of the standard state. Can anybody recall the standard state?
Do you mean? No, I forgot. Sorry.
Is it at 1 atmosphere and 25 degrees Celsius or something?
Closer, but not exactly. So we need to see that for the IUPAC definition, we need to put or confine the pressure at 100 kPa or 1 atm or 1 bar, right? So this is the pressure requirement, but we don't actually have the temperature requirement. Temperature could be any. And then for the gas, that shall be the ideal gas. For the liquid, that shall be the ideal solution. We have not really discussed the exact definition of the ideal solution. We shall have that in today or next lecture. So that is the standard state. What you just mentioned, Doc, is we have this convenient reference always at 298 Kelvin. So if you look at the appendix for all those measurements, we have including the reaction or the formation of enthalpy, then we always have those values measured at 298 Kelvin. So this is quite convenient for us to use in the calculation, but that's not the standard state. So that is the convenient reference. So they are actually different. Okay. So here, let's try to refer the integral to the corresponding standard state, and we will come back to see how do we calculate those standard state. So if we are using, and also the standard state, we try to have this not as the superscript, and so if we try to run the integration from the initial, now the initial is standard state. Then to the left-hand side, that should be the chemical potential of the ideal gas. It's coming from this standard state. To the right of the equation, that is RT, and that would be the log pi naught over pi over pi naught, right? So the mu IID and pi shall be the ideal gas at our interested temperature and pressure. This is the mu I naught And we can safely claim this is also the ideal gas, and Pi naught, that should be the temperature and 1 bar. Okay, and this is of course the ideal gas as well. So that is the equation 3. So that looks like the fun we can have with that equation too. But now if you think about this is purely valid for the ideal gas, but what if we have the real gas? It's no longer the ideal gas. How do we describe the mixture of real gases? So this is why we introduce the fugacity by Lewis. So this concept was introduced by Lewis, and the concept is quite simple. So here, excuse me, for the ideal gas, we use the partial pressure for the ideal gases. And for the real gases, can we find, we're not going to use this partial pressure, but can we find some quantity that very similar to the partial pressure for the real cases? So this is what Gibbs, Lewis, he introduced. He said about, let's try to use a new quantity called fugacity. And fugacity is the relevant or effective partial pressure of that component I in the real gases. So if that is the case, then let's run the equation by looking at the ideal gas equation. So now we simply write down the equation introduced by Lewis. So this is the real substances. And if you compare with the previous equation, we have d mu I temperature. This is ideal gas. Here will be RT, same temperature, d log Pi. Right. So we just replace this partial pressure that is for the ideal gas. Now we have the real gas. Just replace this by Fi, and we define this as the fugacity. So fugacity was not really derived by any mass equation, but we try to compare the ideal gas with respect to the real gas, and we have a new quantity called fugacity.
So chemical potential always describes an ideal gas?
No.
Okay.
Chemical potential is a general definition, and all those equations, including this one, is general for anything.
I still don't understand why we can't use what's the difference between fugacity and chemical potential?
We are going to discuss on that, but first of all, let's make sure that the chemical potential is introduced for any system, any mixture system, whether it's the mixture of components or mixture of phases. There's no need to define ideal gas and use the chemical potential.
Okay.
So we use the ideal gas, simply we need to see, once we have this equation, the equation 1, how do we run those calculations? So that is why we try to look at the ideal gas, try to see how we can simplify those calculations now that we have this ideal gas, the chemical potential as a function of partial molar volume. All right. And once we have the ideal gas discussion, we are pretty happy with the equation 2. But we also realize that this is only valid for the ideal gas systems, ideal gas pure component or ideal gas mixtures, because we utilize this equation to derive this equation 2. So this is why naturally we try to answer, what if I have the real gas mixtures no longer ideal? And apparently we cannot derive that equation very easily. So this is why Lewis said, well, why not just go ahead, come up with a new quantity called fugacity, and we just reference the form for the ideal gas, and we call this is the equation we are going to use for the real gases. So we somehow solve this puzzle for now, but now we need to look at how do we calculate the fugacity, the new introduced fugacity. All right. So if I write down for chemical potential for fugacity, that could be any, whether this is the gas, liquid, or even solids. We should always have those definition of chemical potential and fugacity. So when we use that for the ideal gas, we still use the very general chemical potential and fugacity, but we can also easily simplify those calculations to the partial pressure, but that is only valid for the ideal gas. Okay, so that is sort of the connection between ideal gas and all of the other systems, gases, real gases, liquid mixtures, solids mixtures, or any mixtures you can come up with. So now when we try to look at this is the so-called definition of the fugacity. Now when we look at the fugacity definition, we need to add this condition to complete the definition, which is if you try to push the pressure back to zero, this is moving back to the ideal gas region, right? Then the fugacity could be replaced by the partial pressure. This is how we come up with the idea of defining fugacity. Is that clear?
Yeah.
To summarize, fugacity comes nowhere. It's just out of the comparison between the a real system, whether it's gas, liquid, or solid. Let's try to compare the real substance with respect to ideal gas equation. And there we define, for now, let's call this as fugacity, and we try to figure it out how to calculate fugacity. So we are kind of moving from chemical potential to the fugacity. And the fugacity is kind of defined with the help of the ideal gas partial pressure. Okay. And of course, now we need to move on, need to figure out how do we calculate this fugacity. So moving from this equation 4, then quite similar to the equation 3, where we run the integration from the standard state. Now, if you have a real substance, we could do the same. Again, we are going to use the standard state as our initial state, and then we can try to write down this equation 6. Okay, keep it in mind that we have this d mu I. Again, that would be at the fixed temperature, but this is real. It's no longer ideal. Any real substance, liquid, solid, or gas, would be RT d log Fi. Right? Then we run the integral from the initial to the final. So we have mu I minus mu I naught. This is the standard state. Okay. And then this is the corresponding property of interest for the real substance at the temperature of T. All right. So over here, we try to define some other coefficients. First of all, let's try to look at this. I think I have it over here. No need to repeat that. So let's try to look at the ratio between the Fi So this is Fi at P, right? This is T of interest, and we have Fi, the standard state shall be P is 1 bar, 100 kPa. This is the CNT. So try to compare that ratio, and we define that as the activity. Okay, nothing special. We purely define this AI is the ratio between the Fi naught. I want to remind you that we are very interested in understanding the deviation. What would be the change from the ideal to the non-ideal? So if you recall, this is indeed what we try to calculate what is the property? We try to calculate n residue property. You still remember the residue property? NTP minus NTP. Try to imagine this is ideal, right? So this is the same type of logical flow over there. We try to see what would be the deviation. So here, by defining this activity, we try to understand the same stuff. If AI is very close to 1, then we understand this is quite close to the standard state, where if this is a liquid phase, we can assume this is the ideal solution. If this is a gas, then we can assume this is the ideal gas, all coming out of the standard state understanding. So this is the first, after the fugacity, we define this as the activity. And we also define this here as activity coefficient. So now if you look at the activity coefficient, defined by AI over Xi, okay? So we have this activity, we try to understand the deviation from the standard state, but we also hope that we can look at the system with respect to the liquid phase. So this is why now we try to compare that AI over Xi, and we define this as the activity coefficient. Nothing special, it's just a definition, introducing a new coefficient. So this gamma I would be the so-called activity coefficient. And also we have the last important coefficient, which we call this as fugacity coefficient. So fugacity coefficient is defined as the ratio or deviation from the ideal gas. So if I have Fi, then I try to look at how close that Fi would be from the corresponding ideal gas behavior of Pi. And obviously, if the coefficient is 1, then it's right at the ideal gas. If it's very close to 1, then this should be still very close to the ideal gas. We may think utilizing the ideal gas assumption for the calculation. So that would be a quite nice index for us to understand how far away the system is from the ideal gas. Okay, so that would be the two special cases where we are going to have the activity as 1, then we understand that this is exactly at the standard state. If the fugacity coefficient is 1, then this should be the ideal gas. So we have the 3 busy slides to define quite a few new quantity. So now if we try to look at the whole idea of this, so we define the chemical potential. We move forward to receive the first working equation, chemical potential, d mu I over dp shall be the partial molar volume. Upon receiving this equation, we utilize the equation to calculate the ideal gas. And by calculating ideal gas, we receive the fourth derivative of d mu I. At that temperature shall be RT d log Pi, ideal gas. And that is the end of the discussion along that direction. Then we quickly define this fugacity. So we are moving forward from the ideal gas to any substance, real gas, real liquids, real solids. And no matter how we just call this as the corresponding or effective partial pressure at those real conditions. And that is the fugacity. So one note over here is the fugacity shall have the same unit of the pressure, right? Because it's defined by comparing to the partial pressure. And we also need to have this limit when we push the pressure, moving back to the low pressure region. When pressure approaches to zero, then we are going to return the fugacity to the partial pressure. Okay. After that, we define three different quantities. One is the fugacity coefficient, trying to compare the Fi with respect to Pi. We have the activity and activity coefficients. Okay. Nothing special. Those just the coefficients to see when we have the liquid vapor. When we have that, how do we move from the real condition and try to see how far away we are, the system is from the reference state. So that is the slide to introduce fugacity and some quantities. Now move forward. I hope you see what is coming. So here is still the general equation, and keep it in mind this is the equation for any substance. All right. So we have the equation to correlate chemical potential, and now we have some other correlation to express chemical potential as RT d log Fi. This is again for any substance. Liquid, vapor, liquid, or solid, or mixtures. Okay. So now if we are going to replace d mu I by RT d log Fi, I hope you quickly realize that we are doing nothing but just replacing this chemical potential by the function of fugacity. So looking at the equation 10, I hope we quickly realize that it's nothing special. It's just the manipulation of the partial molar volume and calculate the fugacity. And that shall be the general equation for any substance, right? So this is this is the general equation for any substance. Of mixtures.
Dr. Pong,
Yep.
I have a question about your definition of the fugacity coefficient, because the textbook shows it as fugacity over total pressure.
Well, then you need to pay attention whether it's looking at the component of I.
It is. It's component of I. I'll send you a screenshot in an email.
Yeah. Then the textbook is wrong.
Okay. Okay. Cool.
So you should have this. If you are using total pressure, then
you should have total fugacity. Okay.
All right. We can discuss that and show me the screenshot. So indeed, I have it over here. All right. So if we try to come back to the pure component, let's try to check on this equation of 10 or other stuff we just discussed, because naturally we don't necessarily work on the complicated mixtures, but we can also use that fugacity definition for a pure component. So now if I have the pure component I, then yi shall be 1, because this is one component, right? and the partial pressure of that component is just the total pressure. And the same story, if I have that, then the partial molar volume is just the volume, molar volume of that pure component. So if this is the case, we can simply get rid of, so moving from d mu I, which is RT d log Fi, get rid of those I, and that should be the equation over here. And then, of course, whenever you have the equation for the fugacity, try to think of this as the equation comes together with the fugacity definition. And pay attention that we always have the requirement of the constant pressure. Okay, this is because we have this d mu I over dp at fixed temperature is Vi partial. So we derive all those ideas coming out of this equation. So this is why we still need to carry the requirement of constant temperature over here. And then, like we just derived, or we just received, this shall be the fugacity of that pure component with respect to the total pressure at this fixed temperature shall be V over RT. Okay. One note is those units of fugacity shall be always the same unit of pressure, Pascal, bar, or ATM. So what's the use of this? Well, we essentially we have this chemical potential. We somehow replace the chemical potential by the fugacity. Now we try to see, are we going to change anything for the equilibrium criteria? Again, pay attention. The so-called equilibrium shall be valid for both the phase equilibrium and the reaction equilibrium. I think I need to modify the title of this. So that's three equations: temperature, pressure, and chemical potential. Those would be the three sets of equations we need to satisfy, whether this is a phase equilibrium or chemical reaction equilibrium. And now let's try to see if we are able to replace this criteria by temperature, pressure, and fugacity. I have some little bit of math and try to see what's going on. So we start with the chemical potential criteria at equilibrium. And we understand the chemical potential is a general equation, so this is for anything. If we use fugacity, if we use d log pi, then it's only for the ideal gas. And now we run the integration. This is from the standard state. I try to repeat those conditions because those are quite important when you understand those new concepts and new equations. So when you read the slides or read the textbook by yourself, try to always pay close attention and ask yourself, am I happy with those sub or superscripts? Am I happy with the requirement this is at fixed temperature or this is at standard state? Try to make sure you're happy with those requirements. So this is the equation 14 we have on this slide. So now if we have this equation 14, and let's try to run the integration for the alpha phase for the beta phase individually. So the alpha phase shall have the standard state, the beta phase shall have its own standard state, right? So if we run the integration to calculate the mu I alpha, mu I beta utilizing the equation 14, then this is what we are going to have for the alpha phase. Nothing special, it's just the integration from the alpha phase of the standard state to the current condition of alpha. This is the same of the beta phase standard state to the current beta phase. So now we have this equation 15, all right? So apparently we need to do something in order to further simplify this equation 15. So what we have is mathematically, I can also run the integration. This is from the standard state of alpha to the standard state of beta. Think about why we have two different standard states. Why? Why not they come from the uniform same standard state? Any thought on this?
Is it because it's two different species or whatever?
Quite closer. So the answer is also from the standard state definition. So for the standard state, we only define this P is one bond. Here P is also one bond, right? And we understand that if you are at the equilibrium, the temperature should be the same. So the temperature should be the same, and temperature could be anything. But we also need to acknowledge that we have different species. So we have N1, N2, N3, and in the beta phase, we have N1 prime, N2 prime, and 3 prime. And they are not necessarily the same. So this is why now in order to define the state, we need to look at both temperature, pressure, and the composition. And for the standard state, the pressure should be the same. That is the requirement by RUPAC, by the definition. Temperature should be the same. That is a requirement for the equilibrium, right? But the compositions, we don't have any requirement that they should be exactly the same, right? So this is why now if you look at alpha phase and beta phase, they should have their own individual standard state, all right? So if we acknowledge that, then we can also run the integration from the zero alpha standard alpha phase to the standard beta phase. And over there, I hope you can see that now we are going to have mu I alpha no, let's try to use the consistent note. This is the mu I standard state of the alpha moving from the mu I standard state of beta would be RT log Fi not beta Fi standard state of alpha. Okay. So instead of using the using this system, we try to think of the alpha and beta at standard state. And we utilize that equation to also run for the equilibrium system at standard state. So this is indeed what I have on this slide 16. And now when you try to combine the equation 15 and 16, so now you are going to get rid of the 4 terms of equation 15. And you realize this RT is exactly the same. So you are going to have log Fi alpha is log Fi alpha beta. So there you are going to have Fi alpha is Fi beta. So the reason of introducing the equation 15 and no, slides 15 and slide 16 is mainly to share with you what we have for the two standard state. And if we acknowledge that, and if we utilize the integration over there, then we can derive this equation in the end. So the answer is really straightforward. The fugacity, when we use fugacity as a criteria, it is equivalent to the chemical potential. So now we can safely or officially say this is TP of mu I of the criteria. Now we can use the equivalent TP and FI. Okay. And if we are having the non-equilibrium system, we just need to compare the chemical potential or fugacity to determine and to predict what would be the mass flow. Whether we are going to have species moving from the alpha phase to the beta phase or the opposite. So this is how we are going to determine by looking at the corresponding fugacity or chemical potential values. Okay. So that is a mark to the almost a core discussion of the chemical potential and fugacity. I acknowledge that we have quite a few abstract concepts, but I hope with the slides, with our discussion today and the previous lecture, I hope that would be helpful when you read the textbook. Again, the textbook use a little bit different philosophy and it does not explain all those details. So try to combine the slides and the textbook reading, and hopefully that will make your life a bit more enjoyable. So let's try to look at the other applications. Let's call this as a applications of those fugacity and chemical potential definition. So the first one is, let's try to look at the so-called Raoult's law. We also call this as the very general form of Lewis Randall rule. So the Raoult's law is talking about the ideal mixtures. So this is the other abstract concept of the mixture. So we talk about ideal gas. What is your understanding of ideal gas? If you are going to describe it.
You assume the molecules do not take up space, do not take up volume, and that they don't interact? Great.
That's actually my perfect answer. So no size. No size, no interaction. Or you can reply saying, well, ideal gas is PV is RT, right? That is ideal gas equation. Now let's try to look at the ideal mixture. Ideal mixture is nothing special, but we are going to have the mixture A and B. Okay. If we compare with the mixture over A and A, this is the pure component. If we can have the understanding that the AA interaction is not affected by the existence of other component B, then we call this as the ideal mixture. So they share the volume with P's with the other components. So if that is the case, then we call this as the ideal mixture. We don't necessarily require that we have no interaction. We could have the interaction, and molecules could have their individual size. However, if we try to assume that their interaction is not affected by others, then this is the ideal mixture case. So what's the use of this? Well, the use of it is if we look at that equation 18, then we realize that the fugacity of the mixture, if this is ideal mixture, then the fugacity is proportional to the composition ratio of that mixture. Okay, so if I have this as my fugacity, and we call this as the pure case, and here, of course, this is the mixture. And now you can see that the Fi of A, this is Fi of the pure. In order to calculate what is the fugacity of A in the mixture, the ideal mixture, then we just need to know what is the ratio of A in the mixture. And we multiply this by the pure. Okay. So this is assumption, but of course we need to satisfy the ideal mixture, and then we can utilize this equation 18. And it should be valid within the whole range of mixture. Moving from 0 to 1, we shall have the value proportional to the pure substance. So that is the pure substance fugacity. Okay. And if we try to ask what is that pure substance fugacity, that's coming out of d mu is RT d log F. Okay, and then we are going to connect that with the partial molar volume, and here if this is the pure, then this is just V. Okay, as we discussed just a few minutes ago. Then we can figure out what is the fugacity of the pure substance. So I believe on this slide, nothing special. I just explained what or how to understand the Fi or Fi pure. Keep it in mind that the only difference is we have some other components joining the system to make it as a mixture, and the mixture is also ideal. And I think I have a snapshot to show you what do we mean by the interaction not affected by other components. So the temperature and pressure should be the same. It's just moving from the pure to the mixture. So we, I want to add this note over here. So we say the AA interaction not affected by B, C molecules when you compare the mixture to the pure substance of A. So in reality, this is possible if we are going to have very similar molecules. So I'm not going to discuss too much, but I just want to mention that this holds, the understanding will hold if the components are very similar to each other. For example, if we are going to have nitrogen with CO2, very likely we can understand this will be the case. Okay. On the other side, if I'm going to have water with respect to CO2, then probably I need to worry about the hydrogen bond in the water-water calculation. So apparently, they are two different kinds of molecules. So over there, I may have to check whether I can utilize the ideal mixture understanding. So this very general understanding is if the components are very similar, if they are intermolecular, interactions are very similar, then we can assume this ideal mixture behavior. Okay. So what's the use of that ideal mixture behavior? Here comes the discussion. So now if we think about this interface, try to say in the previous slides alpha and beta, okay? This is a general node to any phases. Now let's try to put it in reality. We are going to have the vapor or the gas. I'm using G over here as the gas, and I have the liquid, okay? So if I have this gas liquid equilibrium, and this is a huge topic of interest to chemical engineering, to any production. So then if we have the system at equilibrium, then we satisfy the temperature of the vapor of the gas will be the temperature of the liquid, the pressure of the gas shall be the same pressure of the liquid, the chemical potential of the gas shall be the same as chemical potential of the liquid, or the fugacity of the gas shall be the same as the fugacity of the liquid. So that we can pick up one, whether chemical potential is more comfortable or fugacity is more comfortable to you. All right. So at equilibrium, we should satisfy the 3 sets of equations or 4 sets of equations, while chemical potential and fugacity are equivalent in a sense. So this is exactly what we have for the equation 19. And now if we can assume this is the ideal mixture, if this is ideal, and if that is also ideal, okay? For the liquid, that would be the only assumption we have ever had for the ideal mixture solution. But here, I want to point out that is not assumed ideal gas. We don't need the ideal gas assumption. As long as we have ideal mixture, the gas phase, like I just mentioned, the nitrogen and the oxygen of the air, and their nitrogen and oxygen, their intermolecular interactions are quite similar to each other. And even I have this at high temperature, high pressure, I can still reasonably assume this is ideal mixture. No longer ideal gas, but it is still ideal mixture. So if this is ideal mixture, then I can try to write down each component with respect to the pure case, right? So nothing special, we just utilize the pure substance fugacity for both liquid and gas. So this is how we introduce yi. So this is the yi of the gas, xi of the liquid, and if we have the assumption of ideal mixture for both phases, then we receive the equation 20. So the reason of talking about all those is I want to sort of explain that why in the petroleum engineering, why we can use this capital K a lot in their calculation. This is if you think about the alkanes and aromatic interactions, they are quite similar in their intermolecular interaction in those similarity. So this is why when we talk about the petroleum engineering for their gas, for their oil mixtures, we tend to utilize the ideal mixture assumption. And if you move one step from the equation 20, then if you take the ratio of x, y over x, then this is the capital K value. And petroleum engineering has lots of data reported with respect to this capital K. Okay. So this is the product we receive out of the ideal mixture understanding for liquid, vapor, liquid, gas equilibrium. And here comes the other discussion I want to have, which is, well, if you look at those, the fugacity of the gas, we can somehow correlate this to the partial pressure. But what is the pressure of the liquid? Okay. So for the gas phase, let me try to write it. For the gas phase, when we have those molecules staying away from each other, and that's a quite easy concept for us to understand. This is the, we are going to produce pressure, molecules are moving around and they are going to interact with the wall, and we are going to receive the interaction force, and we are going to have the pressure. What about liquid? Liquid, we are going to have molecules staying much closer to each other. How do we understand the concept of pressure? Well, in a way, the pressure is still coming out of the intermolecular interactions. When the liquid molecules, when they are moving around, they should also have some force to the volume of the liquid. So the force, if we run the calculation, we are going to receive the pressure. This is one way of understanding liquid pressure. The other way of understanding liquid pressure is, well, liquid molecules, they cannot stay alone as a pure liquid. They should always, if you have the volume, they should always have the boundary over here. And there you are going to have some liquid molecule, not exactly the same as the remaining of other molecules. So this is the saturation pressure we are going to have. So if you have a cup of tea, although this is an open cup, but if even I have a lid, then there will be still the vapor molecules, not too many, but we have the vapor molecules coming out of the equilibrium, right? So over there, we can also express, or we can understand the liquid pressure in a way with respect to the saturation pressure. So this is how we can come up with that equation, very useful equation for our chemical engineering calculations. So we say that at this low total pressure, the total pressure is low. If this is low pressure, then for the gas phase, I hope you realize that we can assume what? Ideal gas behavior. Right? The pressure is low, the real gas phase will return to the ideal gas region. If we return to the ideal gas region, then the fugacity should be replaced by partial pressure. And if this is a pure substance, this is F, because there's only one component. So the fugacity of the pure substance should be the total pressure of that system. Okay, so this is the first equation we have. On the other side, we are using the same understanding, like I just mentioned about the saturation pressure, how we are going to have the liquid phase and molecules at the interface, they are going to vaporize into the vapor phase to maintain the equilibrium. And we are going to stop this transportation when the fugacity or chemical potential will be exactly the same. So over there, we try to look at the equilibrium saturation of the vapor phase, and the pressure or the chemical potential is pi set, and that should be exactly the same fugacity of the liquid phase. Okay, So this is for the vapor at saturation. And this is the low pressure, so this is still Fi set, shall be the Pi set, right, for the vapor phase. And when it is at equilibrium, the liquid vapor shall have the same fugacity. So this is why now I can say this is also the fugacity of the liquid. So I need to point out that the script is a little bit of annoying because we are coming out of the I component. Now we try to also say the pure. If this is the I and the pure, then you basically you don't have this I anymore. You'd better get rid of this Pi. All right, but I leave it here just in case we are dealing with the liquid mixtures. Say I'm going to have water. If I have a case of water, some alcohol, right? This is the liquid phase. This is the gas phase. In the gas phase, I'm going to have also water over there. So the good part is we are able to assume this is the ideal mixture. So if this is the case, then at the equilibrium, I should have the water in the liquid shall be same chemical potential in the gas phase. And if we are able to assume this is ideal mixture, on top of that, plus this low pressure, then this is if. Then we can move on. We can say, well, this liquid fugacity of water would be the composition. This shall be the x of water multiplied by the water saturation pressure. And the fugacity of water in the vapor phase shall be the composition in the vapor phase for water multiplied by the total pressure. Okay. I'm running out of space, but let me write down this also for the alcohol. We shall have the same equation, and the two equations, they are independent from each other because we need to satisfy for the all components. All the components we should satisfy this is the same. This is in the liquid phase. The fugacity shall be the same. In the vapor phase. Now, if we move forward, this in the liquid is x p saturation pressure. We can also express this as 1 minus x water because we only have two components in the liquid phase, right? Saturation pressure of alcohol over there. Similarly, if in the gas phase would be 1 minus y watt multiplied by the total pressure. Okay, this is a very busy slide, but I hope you can take a look at those busy notes and see if you are happy with those concepts. But emphasize, and that would be the last thing I want to have for today's lecture, which is we need to we need to assume this is ideal mixture. This is the first assumption. We need to also assume this is a low pressure or low total pressure. Because we might have a gas mixture, low total pressure. If we satisfy that to assumption, then we are going to use this low pressure form of Raoult's rule. So Raoult's rule itself is coming from the ideal mixture assumption, and we need to satisfy one extra assumption. Okay, I think that we've had enough for today's lecture. Lots of new friends and lots of the ideas moving from the chemical potential to the fugacity and the ideal gas, standard state, real substances, ideal mixtures, and how we are going to have the assumptions. Remember, in the end of the day, we always try to have the specific equations. This is why we derive those concepts, chemical potential, fugacity, for any substance. But in reality, we are only dealing with maybe low pressure mixtures, maybe two component mixtures, or maybe just the steam of pure water, liquid vapor mixtures. So this is why we are interested in discussing those simplified cases with the requirements. Here is ideal mixture. And here we are having one layer of requirement saying it's not only ideal mixture, but also we need to satisfy this low total pressure assumption. And if this is the case, then the final equation is quite easy to understand. And you realize that we get rid of the chemical potential and fugacity, right? We are coming back to the pressure measurement and composition measurement. But behind this equation 21, we have had lots of useful new concepts and discussions along the way. So I'll stop here and we'll come back next Tuesday to discuss other stuff of chapter 10. Okay, that's the end of the video. And if you have any other question, leave the chat or ask for me right now.